So I'll close at this point, and I'll be glad.
You know, a read of history often comes off as people with, people who, authorities who are completely convinced of an idea that then gets dramatically overturned 100 years later or whatever. What do you think mostly has thrown a wrench into so much of the scientific consensus at the current moment? So what, if this is a reality, and it does seem like a very strong argument for it, why has it gone so off track from what the evidence shows?
Well, it's not uncommon, actually, in scientific history. I actually have a backup slide, so I'm glad you asked that. Let me see if I can find it. Okay, here's another example. Scientific consensus is often wrong. This is Alfred Wegener, who proposed a theory of continental drift. And he pointed out that if you looked at the shape of the continent, there's this remarkable fit between South America and Africa, Antarctica, India. And furthermore, if you look at the fossils that you find in these locations, you find the same fossils in South America as you do in South Africa, as you do in India. So all of it points to an original arrangement of the continents together in this one landmass, Gondwana land. And he was ridiculed, he was scorned. In fact, in 1928, the American geologists, the American Geophysical Union, organized a special conference to ridicule Wegener's ideas. They had a prize for who could, pour more scorn on Wegener. And in fact, people still poured scorn on Wegener's ideas when I was beginning graduate school in 1960. And by 1965, he had been completely vindicated by all of the evidence from the ocean spreading centers in the North Atlantic and Pacific and stuff like that. But the people who opposed Wegener, they had no reason to oppose him. He had much stronger evidence than they had, and part of the reason was he fought on the side of the Germans in the First World War. Part of the reason was he was not a geologist. He was trained in, I forgot what field it was, but it wasn't geology. And so the fact that there are these strong opinions on things that are wrong is common in science. There have been, I'd like to point out that, the Salem witch trials, where everybody believed in witches, every one of the judges had a Harvard degree. They all had a Harvard degree. In fact, one of the judges was selling a book on how to detect witches. It sold very well for a year or two. And when the trials finally ended, nobody admitted that there was no such thing as witches. It was just what everybody believed. So there's this tendency of people to, they want to be part of the crowd, of the right-thinking people. And so I think that easily happens, and it's definitely happened with science.
But in particular, what are the arguments that have gone people to turn on? Where have you gotten from?
More questions.
Settle down.
Yeah, maybe we can talk offline. Sure. Yeah.
I have a question about the water vapor feedback. So
Okay. Let me come a little closer because I'm half deaf.
Several times during your lecture, you dismissed the water vapor feedback.
Yeah.
So the physics behind the water vapor feedback is the Clausius-Capron equation, which states that with an increase in atmospheric temperature, the atmosphere is able to hold more water vapor, and this is an exponential relationship between the amount of water vapor the atmosphere can hold and the increase of temperature. So in the results that you showed and during your lecture, you completely dismissed the idea of the water vapor feedback, which in turn means you are dismissing the Clausius-Capron relation. Can you please provide us or present us the proof that the Clausius-Capron equation is not true? My second question is,
Well, I'm kind of Okay, so the question is the Clausius-Clapeyron equation. For those of you who don't know this it's an equation that shows the saturation vapor pressure of water versus temperature. So, for example, water reaches 1 atmosphere of pressure at 100 degrees where you boil it, right? And it's typically, you know, at 0 degrees it might be 6.4 or something like that. It's much, much less. And she's saying, well, the atmospheric water vapor is determined by the Clausius background equation. But no, actually, if you measure the atmosphere, it is not. Actually, it is determined by some sort of average relative humidity, and it's almost never saturated. The relative humidity of the atmosphere only in clouds is determined by Clausius background equation. Everywhere else is different. For example, these big descending loops of the tablet circulation, the water vapor is way less than the
That's why we need professors talking
about it. Out, and it goes,
way better.
You know, like 20,000 kilometers, 20 kilometers, and then comes tumbling down over LA. So it's very, very dry, and it's not even close to the coast. Okay. Well, there are other questions. Yeah. Yeah.
About the cloud coverage you were talking about,
Yeah.
is cloud coverage permanent over a certain area, or does it move around?
It moves around. It moves around.
But the CO2 greenhouse effect doesn't move around like cloud coverage.
That's right. That's right.
So-
CO2. They talk about CO2 as being well mixed, and water is definitely not well mixed. So there's the two extremes. Although near the ground, I can assure you CO2 is not well mixed. So if you look at CO2 with the first few hundred meters, it's
But
not.
when you compare that, doubling CO2 concentration is equivalent to a cloud coverage,
Mhm.
but the main difference there, that's high.
No, doubling CO2 is a few percent change in cloud coverage. You don't have to change it very
But
much.
cloud coverage isn't permanent. It can move around and then
Yeah,
it can
of
go.
course, of course. Then it could well be that the main determinant of the Earth's climate is cloud cover. You know, there are people who seriously propose that. I don't take a strong position on it, but it's certainly plausible. It's more plausible than CO2. Yeah.
I have another question about the feedbacks. In the graph that you showed, you told that you didn't consider any feedbacks. Can you please explain to us why did you not use the albedo feedback? Because we know when the Earth warms up, the snow cover and the ice cover will decrease, and that will increase the albedo, which means the Earth would absorb more radiation. So if you're using a model that does not have the albedo feedback, then it's simply wrong. Can you explain why you did not use the albedo feedback rules?
Well, first of all, let me say, I showed data. You know, I showed the actual warming that occurs and what models predicted. All the models have the feedback in it. All the things you say were in the models, and they don't work. Including my model, which was one of the first in 1982. It was right in the middle of all the other models, and it doesn't work. So you're confusing people between what's actually observed, comparison between what's observed and what gets predicted.
My question was
With
just.
models, you know, so
My
let me
question
give
was
you-
just.
Okay, go ahead.
My question was just on why you are not using or why you're dismissing those particular
But
feedbacks.
because the models don't agree with observation. If they don't agree with observations, they're wrong.
These are physical principles. So if you're not using
Feedback is enough.
Let me put the data on again so that we all know what we're talking about. You know, so that this is an important point.
Oh, this is so entertaining.
I really appreciate that.
Okay, here's the data. Here's the data. This has nothing to do with albedo. It's what has been predicted, the gray bars, what's observed, the red bars. You know, and that's what science is. You know, the mark of a true theory in science is that it makes a prediction that agrees with observation. If it doesn't agree with observation, it's not true. And so these models, mine included, are wrong. You know, because they don't agree with observations, and it doesn't matter which time scale they look on. They're predicting far too much warming, and many of these models have been buttered up with aerosols, you know, to try and get them to fit, but they still don't work. Yeah. Yeah.
Yeah, so, hi everybody, I'm Jonathan. A lot of people in the department don't know me. I'm actually from the other side of campus. We don't care. But I did replicate the digital effect for my middle school science project, so I feel I'm equal to the challenges of this presentation. I just wanted to say, a lot of people feel that bad science is a threat to the academic reputation of the institution and to our education and to our workplace. And if you feel that way, I'm with our grad student union, UAW 286.
What the fuck? Get out of here. Oh, dude, get the fuck out of here.
Get out of here. You brought me, and we're going to be in the hallway after the Q&A if you want to talk to us. I'll bring you
Oh, dude. Oh.
Science, please.
Yeah.
Science questions, please.
Science, please.
You're disruptive. Science questions, please.
Science
questions. This is a PCAM seminar. We are taking science questions. Thank you. Any other questions?
Okay, you're right. Right at hand. I can hear you.
Well, that works. My question is having to do with I'm not strong in this field. So, you showed the pH of water as it was going on with respect to carbon dioxide. So the way you were describing it, you were saying that if we didn't have the carbon dioxide in the air, the pH of the water would be around 11.3. So what is the other counter type of ion in the system that's making the pH so high?
Well, it's because when you weather rock, you weather out more cations than anions. And so if you look at the ocean, there's 2.3 millimolar cations in the ocean, and that would normally be balanced by
charge anions.
OH minuses, right? So that's where the basicity comes from. It's to compensate for all the positive ions that weather out of the rock. So it's called the alkalinity of the ocean. Typical value is about 2.3. You know, it depends on the saltiness. It's proportional to the saltiness. So it has to do with the structures of rocks that the Earth is made.
First off, thank you very much for coming to UCLA. Your data is very, very convincing. What I wanted to ask you was, do you think the key problems that we see with the direction that this climate science is going that you mentioned is because people are not examining this problem over a longer time scale, like you mentioned, to show that historical trend shown that things have been fine even, you know, in conditions that are far more different than what we see today. And again, I want to really thank you for presenting us with observations and not models. I think there's never a circumstance in science where observations should be put below models. So thank you very much for coming.
Thank you very much. I appreciate the kind comment. Are there other?
So it was reported that the average temperature of the Earth's surface increased about 1.5 degrees Fahrenheit since 1880.
About that,
yeah. So with 2/3 of that happening since 1975. So why do you think there's been such a drastic increase?
2/3 did not happen since 1975.
NASA says otherwise, so I'm just curious why you think that.
Well, I'm not sure I have a picture of it, but I just. Well, let's grant. First of all, it's not true that 2/3 is 1975. I mean, but we can argue about that fact. But
no, there's no need for this case.
Well, I just gave the number. Okay. But unfortunately, I didn't put a backup slide on that. Yeah. Yes, sir.
Someone mentioned about timescales of climate change.
Right.
Your scientific opinion was a timescale needed to observe climate change phenomena.
Well, I think if you look at the historical record, climate changes on every scale from tens of years to hundreds of years. You know, sort of 10-year scale is the El Nino scale. We have an El Nino every 5 or 6 years, and that has a huge effect. It caused the rains last year in California. And then you have sort of 100-year, several 100-year scales. I showed you the drought, the mega drought from 900 to 1300 in California. That also, by the way, corresponded to the colonization of Greenland by the Norse, so they were probably connected. And then there are 100,000-year time scales, which is the time scale of the glacial, interglacial cycle. And then there are even older ones, you know, those associated with plate tectonics. You know, we're basically in an ice age now. And many people think it's because the the equatorial seaway has been closed, with the closing of Panama. That's roughly when the ice age started. And that, that's even longer time scale. It's 50 million years, something like that. So that it occurs on every scale. Just like, we live in a world that's hot in the middle of the day. It's cold at night. So the time isn't stable. The idea that it's stable is just crazy. It's not.
Can I just suggest something? Anybody that has questions that Professor Happer is willing can ask them. But if people have to leave, don't have any compunction about leaving now, because we're well past.
Yeah, please don't be held up by questions.
Yeah, so, I mean, fluctuations, daily fluctuations and things like that are definitely normal. So I wanted to ask about when people talk about a change in 0.5 pH of the ocean, they're usually talking, I think, about a change in the average pH, right? So what do you think that would do? And then in that case, what do you attribute the depletion of the coral reefs to, if not to climate change?
Well, there's a lot of talk about the coral reef, but the big effect on coral reefs is really the El Nino cycle. So, for example, in Australia, when you get coral bleaching, it's typically during the El Nino cycle when
this is really fun. Every so often.
It's been happening since the world began, and you can actually do geology of the coral reefs. And, coral reefs, they like to be, I don't know, this deep, that's the optimum depth, and they grow. They try to get to the optimum depth. You've got tides, and you've got these bunkers, things like that. Every now and then they look out there. If they're lucky, they simply bleach, and then they get the little symbiotic, algae back as soon as conditions improve. But they may die. But even if they die, it gets recolonized very quickly. There's coral slugs all over South Pacific. So it's not. Oh yes, I think so. In fact, if you look at the carbon dioxide increase, it's only half of humans allow. So the big question is, where does the other half go? Yeah, big mystery. The oceanographers swear that it's not in the ocean, but I'm not so sure. But they may be right. Yes.
You mentioned in one slide that at 1,000 or 2,000 ppm carbon dioxide, that plants and animals were able to flourish. But can you also mention if the carbon dioxide concentrations would rise to that level today, what would be the sea level compared to present sea level? And if we see a carbon dioxide concentration of that much, and with the sea level rise we would observe under such conditions, how much land would go under sea and how much human civilization would go under sea?
Okay, well, I have some backup slides on that. I will show you. There's a lot of talk about sea level rise. So let me show you some data again. Okay, here's sea level since the last ice age, and this is meters, so what have we had? 140 meters, 400 feet of sea level rise since the glaciers started to melt over Canada. So that's a huge rise, but it was mostly finished by 6,000 years ago. Since then, we've had very, very slight changes, and actually it sometimes goes up, sometimes goes down. Here is an example. This is from the IPCC report. So this is the sea level trend per year, and you see it fluctuates up and down. It was rising rapidly in the 40s, this is the Dust Bowl era, and it dropped again in the 60s. It's risen a little bit recently, but there's no sign of any acceleration, any real acceleration of sea level rise, and you can bet that since this is from the IPCC, they did everything they could to make it look alarming. And here is actual tide gauge measurement from Denmark. If you go to the Baltic, if you go sufficiently far north, the sea level is dropping very rapidly because the land is rising from the weight of the ice that melted, 12,000 years ago. Go south, the land is sinking because it's a seesaw effect, and this is supposed to be roughly in between. So this is thought to be geologically stable, but you can see the rate of rise. It's about 1 millimeter per year. There's not any sign of any acceleration. And every tide gauge in the world that I know of looks like this. It's a straight line, either going up, going down, but no acceleration. Yes?
So let's just say that as your observations are showing, that CO2 in the atmosphere and the production of CO2 really does not matter climate change at all.
Right.
Is it still sustainable? Coal fuels and fossil fuels are not an unlimited amount. Therefore, you were suggesting that we shouldn't spend all this time trying to come up with alternative methods of fuel because carbon dioxide isn't.
Somebody said that. Somebody said
that.
I said on mitigation, and mitigation means that
scrubbing.
You sort of close down all fossil fuel plants immediately, and but I'm 100% for finding better, ways to get energy. Fusion, I hope, works. I mean, we've squandered a lot of money at Princeton if it doesn't work. Yeah, for which I'm very sorry, but it was for a good cause.
So in the long run, you believe that fossil fuels are not a...
They'll run out. As you say, of course they'll run out. I mean, they'll last for hundreds of years, but sooner or later they'll run out, and I hope the human race lives a lot longer than that.
Yeah. You've obviously discuss the benefits of CO2, but in burning fossil fuels, especially coal, there's a lot of sulfur compounds, and you get a lot of other acidic compounds.
Yeah, thank you. Yeah, for raising that issue. It is really true that when you burn fossil fuels, there are real pollutants. CO2 is not one of them, and water vapor is not one of them. But NOx, nitrogen, oxides of nitrogen are very bad for you. Sulfur oxide, who wants to live in, sulfuric acid, so fly ash, it's nasty, it gets all over your clothes. So those things should not be permitted. So I'm 100% for regulating those to a sensible level. You shouldn't over-regulate them. There's a sensible level where it's sort of ambient levels, and that's where you should stop. But you're right.
We're focused on CO2, but of course
there are real pollutants that need to be regulated, and I do support that regulation very much. Yeah. Yeah.
I believe this was essentially the heart of the question earlier by the lady over there. But essentially, so you're talking about the Clausius-Clapeyron equation. She was talking about the Clausius-Clapeyron equation, and if I believe I got the heart of her question was that maybe water vapor is more dependent on ambient temperature. Like the amount of water vapor in the air is very dependent on average temperature, whereas carbon dioxide, you see what I'm saying, that cause is temperature for water vapor. What do you feel are the major determinants of water vapor, atmospheric concentrations of water vapor, if not temperature, if you're concerned about it as...
Well, the other, by far, second most important thing is the wind field.